I extend a warm, enthusiastic welcome to each of you. Tonight, we come together for the final session in our 5 to 5 talk series, and what a journey it has been. Throughout this series, we delved into the wonders of science, discovering fascinating insights and engaging in thought provoking discussion. As we conclude this chapter, we are thrilled to present an extraordinary topic from Big Bang to bolometers, the hunt for the primordial gravitational waves. This evening, we will embark on an intellectual voyage that spans the origins of the universe to the sophisticated tools used to decode its secret. We are privileged to have with us an exceptional resource person to guide us through this awe inspiring journey. Your presence and curiosity make this session all the more special. So, once again, welcome to everyone and let us dive into the mysteries of cosmos together. It is my absolute honor to introduce our esteemed guest for this evening, Dr. Anto Lonappan. Dr. Anto is a postdoctoral research fellow in cosmology at the University of California, San Diego. His expertise lies in studying the cosmic microwave background, the ancient light that holds the secrets to the universe's origin and evolution. As a part of prestigious collaborations like Polar Bear, Simon's Array, Simon's Observatory, Lightbird, and CMP-S4, Dr. Ando's work has been instrumental in unraveling the mysteries of the cosmos. His research explores the dynamics of the early universe and its connection to phenomena like gravitational waves. Dr. Ando is also an alumnus of SB College, Chakanashiri, a journey that has brought him from Kerala to one of the most advanced scientific institutions in the world. Tonight, he will take us to the topic from Big Bang to bolometers, the hunt for the primordial gravitational waves, offering insights into the fundamental physics that shapes our universe and the technologies that help us explore them. Dr. Ando, it is an honor to have you with us. The session is yours.
Thank you very much. Can you hear me properly and see my screen very well?
Yes,
Can
sir.
you hear and see my screen?
Yeah, it's visible.
Okay, full screen, right?
Yes, yes.
Yeah. So first of all, I thank you uh, all the organizers for arranging this 5 talks. I have been to like couple of sections before. I really appreciate the work the organizers uh, put to like arrange this kind of talks. As Siddharth mentioned, today I'm going to talk about one of the hot topics in the universe, how we gonna detect the Big Bang. So the Big Bang has already been indirectly detected uh, by uh, by detecting the CMB, the cosmic microwave background. You can see like a band of cosmic background here. Um, so this is an indirect very indirect evidence for the Big Bang. But what we are trying to do with all those experiments here, Simon's Array, Simon's Observatory, CMBS4, and the Lightbird, what we are trying to do detect the direct evidence of the Big Bang, and that's something called primordial gravitational wave. The primordial gravitational wave is not the astrophysical gravitational wave. So I will explain all those things in few minutes. So this is what we're gonna explore today. So I will start with the very basics. I'm not going to put all the equations and all. So things will be like very pictorial and very simple. So I will try to explain what is light, what are the properties of this light, and where we are in this universe in time and space. When it comes to time, we are looking back into our history. Then I will shortly explain what is the expanding universe, why our universe is expanding, and Then we will go to the picture of our baby universe, which is the cosmic microwave background. And from there, we will try to understand how the universe was born. Moving on. So, what is light? So, one of the classic explanation of light is an electromagnetic radiation, which is transverse wave. So, what does it mean by transverse? The electric field oscillates in the 90-degree orthogonal to the wave motion. Uh, but light is not just an electromagnetic wave; it also have like a particle nature. So this is called wave particle duality. So I think these are covered in 12th standard or like bachelor's in bachelor science. So that's the fundamental nature of light. Light is like electromagnetic wave and also like it behaves as a particle. And there is some important property of light which is called polarization. So as I showed you in the previous slide, the oscillations of electric field. So if an unpolarized light, you can find this oscillations in all direction, all possible directions. As you can see here, the electric field will oscillate in all directions. But what is a polarized light? Polarized light can only have a single plane oscillation of electric field. So it has like many practical use. So for example, if you go to like a 3D movie right nowadays, previously they were like doing like some color filter. Right now they all uses polarized filters. So in one of your one eye covers like a particular polarization angle and another one is different. So next time when you go for a 3D, take this thing and try to rotate it, you can see the difference. Um, so yeah, so the light can be polarized or unpolarized depending on what are the physics. Uh, and the most important thing I want to stress today is the speed of light. Speed of light is like around 300,000 kilometer per second, uh, which means something. And what is that? So if you are looking yourself into a mirror like 2 meter apart, so what you are seeing is your past. You are never, you cannot see your present at all. So when you, next time when you look into the mirror 2 meter apart, think that you are seeing someone 13.3 nanoseconds away. Let's expand the scale. So it will take like 8 minutes to the light from the sun to reach our earth. So in any stupid reason, the sun got disappeared from our universe, us like an earthers, like we will only know like after 8 minutes. So when you look into the sky, when you see the star, whatever light comes from the sky, next time you have to think you are seeing the past, you are not seeing the present. So the light which coming from the tingle stars, it might not be there right now. It might be like disappeared like years before. Maybe this star is going to be like light years away. So it will take like light years. I mean, at least like 1 or 2 light years to understand whether the star is there or not. So because of the speed of light, we are looking into the past. Now I want to show like how vast our universe is. So this is our beautiful Earth, one of a kind, and this Earth is belong to, as you all know, the our solar system. So like Earth is here, one of the tiny planets in our solar system, and the solar system is I mean, solar system belongs to the 1/3 of the Milky Way galaxy. So you can see here, this is our Milky Way galaxy, and the sun is somewhere here. So we are going to be somewhere here. So we have like a nearby galaxies. Uh, our nearby galaxy is called Andromeda. which is cartoonized here. So like after 6.5 billion years, like we will the Andromeda and Milky Way are going to like collide each other. So all the Andromeda galaxy, Milky Way galaxy, and there is like another galaxy in the background. These galaxies belongs to like a cluster of galaxies, which is called Virgo cluster. So you can see that the Virgo cluster here, and the Virgo cluster. This all are called Virgo supercluster. So there are clusters of cluster around, and this is called Virgo supercluster. So the entire galaxy, each points you are seeing is galaxies, and everything belongs to like a Virgo supercluster. And the Virgo supercluster belongs to another supercluster, which is called Laniakea. So you can see here the Virgo cluster is here. We are somewhere like here, like very, 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 very tiny. And this all are the nearby galaxies. There are at least like 100,000 galaxies in this picture. So those are our neighboring galaxies. So if we zoom out further, so this is a picture where also it has like time information. So you look into the y-axis. So if this is the y-axis, this is also this is in the time, and whatever we are seeing is in this is the present. So we can see that our Virgo cluster is here. When you look back into the time, you can see that all those galaxies clumping together, which was like close together, and we go back, and we will see a cosmic micro background layer. It is uh, depicted in like yellow line, and then there was Big Bang. So an this is to show that how we evolve. So we will explain it more detail in the coming slides. So now let's look our universe in time. So it also tells us about our history, our own history. So currently we are in Earth. So 300,000 years back, the first our ancestors walked in the Earth, Homo sapiens, and around 3.7 billion years ago, we have the first life in the planet, coming from the single organisms, and 4.5 billion years ago, our planet Earth started to form. So this is roughly the number which I'm giving, also applicable to other planets at the same age of us, our Earth. Then around 4.6 billion years ago, we had our like solar system. The solar system started to form, and roughly like 10.8 billion years, the galaxies started forming, and 11 billion years ago, all the large scale structures you see in the previous picture started to form. So from 13.8 billion years, our cosmology, our universe, our cosmos started evolving. And from where it got evolved, uh, it was from the Big Bang coupled with inflation. So if you are asking whether it was like inflation first, Big Bang first, so it's we cannot say like indistinguish this happened like at the same time. So sorry. Yeah. So before that, the time begins. So we have no idea what's happened before, but the time begin when when the Big Bang has happened. So where we are now. So looking back, we have like cosmologies in culture. We have like mythology, religious cosmology. But science started in a very scientific way, which is called proposal of theories, experimenting, observation, and hypothesis testing, which is the physical cosmology. And physical cosmology have an short history. In second century, the Ptolemy, with the physics of Aristotle, proposed a Earth-centered cosmology. So the problem for this cosmology was there are different laws for the Earth and cosmos. So the motion of Earth is having a different equation, where the moon have different and the sun has different. But 14 centuries later, that means like 16th century, a Polish astronomer Nicholas Copernicus, he observed and figured out like a sun-centered cosmology, and this uses physics of Newton, basic Newtonian physics. And in this cosmology, everything was like universal. So same laws for everywhere. So Earth, Sun, every object, stellar objects follows the same laws, which is Newton's equations of motions. But 4 centuries later, in 20th century, Edwin Hubble uh, gave like an evidence for a universe which is changing and evolving, which is called expanding universe. And this cosmology is the current cosmology according to the recent evidence, which is called the Big Bang cosmology. And this is based on physics of Einstein, which is general theory of relativity, special theory of relativity, and all. So we gonna talk about uh, the expanding universe. So here is the Hubble. You can see Hubble. He published his observation in 1929. This is his observation. I'm going to explain it. So what he was trying to do, he was looking into the neighboring galaxies, and he took two fundamental things. He took two fundamental readings. One is the velocity of that galaxy, how fast it is moving from us, and how far it is. So these are the two things he have observed. So he put it in the graph. So in the x-axis you can see distance, and the y-axis you can see velocity. And this gave like a clear picture of what's happening. So us, and he put it as an equation, v equal to h naught times the distance, which is called Hubble equation, and h naught corresponds to the Hubble constant, and Hubble constant will tell you how faster our universe is expanding. That the rate of change of expansion is what the Hubble constant tell you. So what he found was interesting. So farther the galaxies, faster they are moving. So during this time, uh, so scientists start thinking reverse engineering. So if everything was expanding, what was happening previously? So they started reverse engineering how our cosmos work. Right now, I don't want to reverse engineer. I will start from the beginning. So I will start in a very story way. What was happening all those time from the moment time began to the present days in a very short way. So this picture is a good representation for that. So in the beginning, there were quantum fluctuations, or called primordial fluctuations. And to these primordial fluctuations, inflation has happened. And all those things are together probably called Big Bang. So when the inflation has happened, the space got expanded tremendously. So in other words, you can simply imagine that, consider like a mustard seed in your hand, and within 1 second it got expanded like 6 times a football stadium. That far. I mean, I'm just giving like a random analogy. This is not scientifically correct. So that fast the expansion happened. And after this expansion happened, our universe was very hot, like thousands of Kelvin hot. As part of the expansion, uh, our universe started cooling down. And during this time, there were like electrons, protons, photons. So the photon is like a funny guy who is like hitting around. It hits like electron photons hitting around. He have no escape from these hittings. So we call it as like baryon photon fluid. But the reality, you can imagine that the photon have no escape. So it's just like colliding with electron and protons. So as the universe cooled down, the electron and proton started forming hydrogen. And this is the time which we called recombination. So electron and proton started combining to hydrogen atoms, and the photon got completely free. The photon started free streaming, and that is the photon which we currently detected and call as cosmic microwave background. So after that, let me put it another way. The universe was so opaque, no light was coming out of the universe. But on a sudden, after the recombination happened, the photon free streamed and the universe become transparent. But later, uh, the gravity pulls, the first stars formed. From the first stars, the light came and reionized those electrons, those hydrogen atoms. That's why it is called reionization. So that's something like we can only see. So before reionization and the time of the emission of the cosmic microwave background, we call it as something called dark age because we couldn't see anything during this time. And now our universe is like ionized. We can see things. We can see like everything around galaxies, super clusters, galaxies, everything. So right now we are in this stage, and still our universe is expanding. The currently why it is expanding, it's not because it may be because of something happened previously which we have no idea. We will talk about it in the later slides. So this is the almost like a scientific story of our universe, the evolution of our universe. Now we will talk about the cosmic microwave background. So I want to start with how the CMB is discovered, and it was an accidental discovery. So around 1960s, Penzias and Wilson, there were like two um, radio astronomers. So this was the mission they used. So this is the radio telescope, which is called a Horn telescope. So this entire platform will rotate to 180 degrees, and the entire platform will rotate in the other way in 360 degree. So they were trying to observe radio galaxies, the galaxies which emits radio signal. And these people were getting a constant noise wherever they look, whichever part they look in the sky, they were getting some constant noise. So they were like highly troubled by this thing. So once they really thought, this noise is coming from the poops of the bird, which is here. So they started like rubbing all the poops of the bird to remove that noise. But whatever they did, the noise was still there. At the same time, parallelly in Princeton University, these people like Dick Peebles and Wilkinson, they were reverse engineering whatever things we were telling previously. They were theoretically doing everything. So they were like planning to make like a microwave receiver to detect whether there is like a remnant or relic photons from the Big Bang. Uh, so in scientific community, when we publish our papers, we send it to like referees. So these people send their papers to like Bernard Berg, who was in MIT. After reading this, Bernard Berg already know the issues of Penzias and Wilson. Berg called these guys and tell, okay, there is something going to happen, and there is going to be like a huge. And these people talk each other, and they figured it out. So whatever the noise they were getting was from the cosmic microwave background. And these two people, so Penzias and Wilson got Nobel Prize in 1972 for the discovery of the cosmic microwave background, and Jim Peebles have received Nobel Prize in 2019 for all his theoretical work, which paved way to the discovery of cosmic microwave background. So, what is cosmic microwave background? It's the ancient light in the universe, first light in the universe, like relic of the Big Bang. I mean, you can put like many words for this thing. So, if you have seen this in the television, uh, this noise you see it in the television when we had those antennas, you were seeing like 1%. You were seeing the birth of the universe. Or fun fact, so if you just construct 1 centimeter cube just in front of you, you can count like 400 CMB photons if you have the instrument for that. So you look around, you will see CMB photons. In other words, CMB photons is everywhere around you. You're everywhere. So we are in the bath of CMB photons. So now I will tell you about how the CMB photons is the picture of our baby universe. So this is how it will look. If you look around the sky, you see like everything is same value. So why why it is oval? I will show like a slide towards the last why it is an oval shape, but this is actually the spherical projection in a two-dimensional space. So I will show a animation for that later. But if you so in 1919 around 1960 1970, I guess, NASA have launched a mission which is called Kobe, and Kobe had like a instrument called Firas. So the Firas was equipped to measure the cosmic background, microwave background in all frequency channels. So they collected the data from 30 gigahertz to like over like 700, 800 gigahertz, and they put all the intensities coming from the each frequency channels, and this was like a perfect black body spectra. In scientific way, we say Planckian spectra. So what we was seeing that every point you look at each point, we are seeing same thing. And that's why I put the slides as like homogeneous and isotropic. So homogeneous means every point is same. Isotropic means any direction you look, you see the same thing. And when we fit this spectra, we get like an equivalent temperature, which is like 2.725 Kelvin. So this is the present time. But at the time of emission, the photons were like at 3000 Kelvin. So now let's see like from the isotropy, everything is same at every direction. How we gonna get something not isotropic? That's something called anisotropies, which is not isotropy. You will see in couple of seconds, this is not going to be like same everywhere. So consider this as a picture, and I subtract the mean value of every pixel, then I will get something like this. And the difference of each pixel would be something around 3.35 millikelvin. And why is that? This is called a classic Doppler effect. I know that you are like very well known for the Doppler effect. This is something like we experience when we stand in the railway station platform. So why, and same thing happened to the light as well. And why it is happening? Our Earth have like a local motion, which is one of the hemisphere of our Earth moves opposite towards the CMB photons come, where other one moves towards the CMB photons. So we have like an anisotropy here, and this is coming from the movement, and we have figured out how fast we are moving with respect to the CMB photon, which is like around 370 kilometer per second. So now you take this value, the mean of this value, and you subtract that. And there you will see the beautiful CMB, and you can see that it's no more same value. It has some sort of signal. It has some sort of it has some sort of values, and the values is only differ in 10 microkelvin. So you can see it as like one part of 100,000. So this is the picture of our baby universe, and the tiny spots you are seeing here become galaxies, superclusters, everything. That's the evolution of our universe. Our universe was something like this, and we've evolved to what we are seeing right now. So how this sports, you have seen that blue and red spot, how the sports are created. Let me give you like a very short explanation. So in the beginning, we had quantum fluctuations, then inflation happened. So when this tiny quantum fluctuations, which we cannot even see, become density fluctuations, which is something called macroscopic density fluctuations. So how you can see is a density fluctuation. You can see that matters clumps together at some part of the space, but there is void somewhere here and there. So you can easily imagine it as like a marketplace, or like a fair place where there are some attractions, or where there are so much sale, the people comes together. Similarly, if there is like a gravitational attraction somewhere, the matters comes together. So that's a perfect analogy for the density fluctuation. And so the density fluctuation was there. Then the recombination happened. Remember, the electron positron become hydrogen atom, photon got free. So the first atom formed, the universe became neutral, the photon left the plasma. So whatever the density fluctuations were there, this photon took a picture of it. So whatever density fluctuations were there, the time when the photon left, the CMP took a snapshot. So CMB is a snapshot of those fluctuations at the time when it left the plasma. So now let's talk about hot and cold spot bit more. So you see blue here, you can see the red spot here. So red spot is called cold. Why? It has like low energy because of high density. Let me explain. So consider that we have a potential well. So potential well is something called a high mass density air, and the photon was coming out of this area. So photon has to climb up to escape this potential well. So this way the photon loses the energy, and that's how this become cold. But whereas where there is no low density, photon didn't lose any energy, so they were like simply hot at that time. So just a recap. So we had quantum fluctuations, inflation has happened, um, inflation has happened and density fluctuations were created, and density fluctuations imprinted CMB anisotropies. Now let's decode how we gonna understand these things. So this is like a very classic mathematics and standard methods which we use in different applications, invented by Joseph Fourier, a mathematician in 1700s. So you can see that this is a time series or like a music, which have like a time. So when we apply the Fourier transform, we can see it as in a frequency domain. So this is actually the sum of these three waves, three frequency waves. I mean, this frequency is higher, this is lower, and this is much lower. And this is called the spectra, frequency spectra. So where you can see that the amplitude of this spectra is like higher according to the frequencies. A similar thing will happen to the space as well. So we were talking about something time series, but now if you are applying it to the space, then this will go to space, and the whatever we are seeing won't be like frequency. That would be the scale, how much fluctuations are there. So now let's decode CMB a bit. So we have the CMB, we subtracted it, we got like first anisotropy, which is coming from the motion of our Earth. We subtracted that as well. Then we see the beautiful CMB, which is something around 10 microkelvin. 10 microkelvin means one part of like 10,000, 100,000. And we see how the homogeneous universe become isotropic universe become anisotropic. And then we apply the Fourier transform to this picture. In reality, Fourier transform won't work. Why? Fourier transform is like limited to flat space, but CMB is coming from a spherical. We are seeing around our globe, so it's like spherical. So this is an equivalent of a Fourier transform. Never mind. So this is the spectra of what we are seeing, and this spectra will tell you about our cosmology. This spectra of like distinct shape, which will tells us about the age of the universe, what are the content of our universe, the curvature of our universe, many more things. So let's dive into what is our energy budget of our universe, which is coming from our cosmic microwave background. According to the current data, with 95 percentage confidence level, we have like 70 percentage energy dominated by dark energy, which we have no idea what is dark energy is. But only one thing we know, that dark energy is responsible for the current expansion of our universe. And 25 percentage we have dark matter. Again, we have no clue about like what is dark matter is. We are hunting down both dark energy and dark matter in a different scenario, and that's a separate talk itself. I don't want to include that in here. So then we have like ordinary matters, just 5 percentage. And what are these ordinary matters? So the ordinary matters sees uh, composed of everything what we see, including us, me, and you guys, our galaxies, dust, everything. So just 5 percentage. Rest of like 95 percentage, we have no idea. So now, as I told you of the properties of light, it's polarized. CMB is also polarized. So polarization can be done differently. It can be reflected, it can be scattered. So in the right hand side, I'm seeing a animation how CMB got polarized. So consider that there is a hot region here and there is a cold region here. and an electron here. So the photons from hot and cold region comes and it gets scattered by the electron, which is called Thomson scattering. Such a photon will be linearly polarized. And there are like two patterns in the polarization. One is called E mode polarization. So if you are looking at the cold and hot spot, you will see something like this pattern. And also there is something called B mode polarization, the polarization vector will look like this. So we have detected E mode polarization with a good precision, but we haven't detected the B mode polarization yet. And that's going to be the direct evidence of the Big Bang. Why? Because B mode polarization can only be created by a gravitational wave, which was created during inflation. So if inflation has happened, that tremendous energy have created some gravitational wave, and this gravitational wave have interacted with the density fluctuations or like at that time, and during the CMB emitted from the primordial plasma, this polarization pattern have been imprinted to the CMB, and that's why uh, all the CMB experiments now are looking for detecting the B mode polarization. That will give the energy scale of the gravitational wave, which is called the primordial gravitational wave, and that will give the direct evidence of the Big Bang. So, power spectra. So this blue line represents the temperature power spectra, which I already showed you before. Also the E mode. So these are the data points which we have secured during last CMB observations by different experiments, but we haven't detected the B mode power spectra. This is an expected B mode power spectra, which we don't know like whether it exists at that level, but this is an expected B mode power spectra, which we haven't detected. So what are the challenges? So it's not that simple to like detect the B mode. There is that it comes with a big challenge, and the important challenge, as you can see here, is that you can see a sort of forest there, trees there, but you are completely obscured by the dust. And same thing too for the B mode as well. Our galaxy is our first challenge. So as you know, we are somewhere here in the galaxy. Um, so this is polar bear. So I think Siddharth pointed that I was working with polar bear previously. Yes. So this is our polar bear experiment, and you can see the band of our Milky Way. This is a picture which we took from the Atacama. Uh, so this is the band of our Milky Way, and yeah, that's the first challenge. So the dust particles in this galaxies and the high energetic electron which goes around with the magnetic field creates something similar like cosmic microwave background, which is like a foreground. That's called foreground to the CMB. So here I am showing the power spectra. So this is the E mode and this is the expected B mode. And you can see the power of the synchrotron radiation and dust radiation, which is much higher than the signal which we are looking for, the B mode. So first challenge is galactic foreground. The second challenge is gravitational lensing. So what does it mean? So while the CMB travels towards us, the CMB is lensed by different galaxy cluster of galaxies. So you can see it as an optical lens. Optical lens deviates the path of the photon. Similarly, a gravitational force, gravitational potential will also make a photon deflect. Uh, so what's so this is a cartoon of that. So CMB photons coming, it get deflected by a supercluster, so which we are observing. So we cannot observe an unlensed CMB. We will always observe like a CMB, which is lensed. And what's the big issue of this? So this is the expected B mode, but you can see that we have like a lensing B mode, which is same, which is much higher than the expected signals from the inflation. And this is the second challenge. And this lensing B mode we have already observed. These are the data points which we obtained from various experiments. And the final challenge is the sensitivity. So the polar bear was sensitive at up this level. Simon's array was sensitive to this level. Then the Simon's observatory, which I am working right now, is like sensitive to this level. The CMBS4 is a ground-based telescope which is going to come like in 2030, which is like lower than Simon's observatory. But Lightbird is a satellite mission which is completely looking in a different place of the signal regime, which is here. Um, so yeah, these are the experimental challenge, the sensitivity of the instrument. So now I will talk about how the CMB is observed. So we can observe CMB from space and ground. So here in this case, we are observing from L2. L2 is like a 1.5 million Kelvin from Earth in the opposite direction of Sun. So we will put the satellite here, and we will observe our CMB. So this is how the CMB is observed. And this will explain you why all the pictures before is oval, because we will observe the CMB in a spherical way, then we project it to the 2D plane. Yeah, it will show you right now. Yeah, there it is. This is how we observe, and this is how way it projects. And the band you see here is the galaxy. And how we will observe in ground. For the ground, we have like more challenges. We have atmosphere, but we use the fact that sky is rotating. So we will put our telescope in the constant elevation. Then we go to and fro, left and right, thereby creating a patch. So you can see it here, how this telescope is moving. It go to and fro. That's how we observe CMB from the ground. This is polar bear, by the way. And now I comes to the last slide, bolometer. So the telescope which you saw previously is housed with this thing, this telescope, this optical tube. So the photons will come through this thing. The entire thing is kept in a cryogenic system. So there are like different layers for this. The first layer is like at 50 Kelvin, then it comes to 4 Kelvin. This is the focal plane. And the focal plane um, is kept at like 100 millikelvin. 100 millikelvin. And the focal plane composed of something called lenslet array, and you can see the lenslet array here. There are like bubbles. Every bubble corresponds to like 2 bolometers. And this is the antenna, so which is like very very tiny. You can see it's like 1.5 millimeter. And these are the bolometers which we are seeing here. So all those things are the readout components. And the bolometer is something which change the voltage when a photon hits it. So it absorbs the photon and it changes the voltage. And this change of voltage is something like we record. And from this voltage, we construct all those maps. By this, I am concluding. Um Thank you very much for the opportunity. Just I want to conclude with a saying of Carl Sagan. We are a way for the cosmos to know itself. Thank you.
Thank you so much, Dr. Ando, for the fascinating and enlightening talk. Now we would like to open the floor for discussion. If anyone has questions or would like to share their thought, please feel free to do so. This is an excellent opportunity to engage with Dr. Ando and dive deeper into the captivating topic.
Hello, hello.
Hi.
Am I audible?
Yeah, yeah.
Uh, yeah, I'm Siddharth.
Yeah. Yeah.
Okay. What I would like to ask is, what is your take on Hubble tension, which is a problem in cosmology?
Um, yeah, it's my personal take. I don't have like a personal take. It has to come from a scientific fact. So to the audience, what is Hubble tension is so CMB. So I have so what CMB, the cosmic microwave background, gives like a uh, Hubble value, which is something around 68. But when we look into the galaxies from this figure, we get something around 74. And this is something, there is like a 5 sigma different, and this is called Hubble tension. Uh, there can be a new physics, which we don't know why this is happening. The early universe is giving a different value, and why local universe is giving a different value. So there are two options. One, there is a new physics. And second option is maybe there is an issue with our experiment. So we are not in a stage to comment either of it. So we have to wait for more instruments to come. For example, there are LSST is coming. Another experiment called DACE is coming, which are looking for the dark energy surveys. And we have to wait for these experiments to come with a high resolution data to test like whether this is right, or if there is a real tension, otherwise, or it's like a instrumental or statistical fluke. We have to wait. So
Okay.
I am
I
uh,
know.
I'm not in a stage to say that okay, there are other, there are certainly there are like different early universe models which can accommodate this thing. But I don't think so. We have anywhere like we don't have like a good evidence to support that.
Okay. Thank you. I also have one more question. Have you heard about calculating Hubble's parameter using gravitational waves?
Yeah,
Is it possible? Can
yeah,
you?
definitely. It is definitely possible. So, a gravitational wave is going to be a next generation probe for the cosmology. So, right now, the problem with the gravitational wave which we are talking is completely different than the gravitational wave which I was talking about. I was talking about the primordial gravitational wave. The gravitational wave we were talking right now is the astrophysical origin. Uh, this gravitational wave, a new experiment is proposed, which is called LISA. This is going to be like a telescope out in the space. So with the LISA, we will able to detect more events, gravitational events, and not just gravitational wave. So there is a counterpart for that, electromagnetic counterpart. So if a black hole merge, or like a neutron star merge, the gravitational wave is produced. At the same time, the electromagnetic wave is also produced. So we can detect gravitational wave. After the same time, we can also see the electromagnetic counterpart of that. So by comparing these two data, we would able to uh, estimate the Hubble constant in a much better way. That's going to be like an independent probe, and yeah, we can wait for that. Maybe it will take like 10 to 20 years, but yeah, we should wait for that. But
Okay,
again,
thank you. There is a question in the YouTube chat. Okay, I will read it out. Sir, have you looked into a research paper pointing out the possibility of a second Big Bang that might have occurred, creating the dark matter after the first Big Bang, creating the ordinary matter? You got the
uh,
question?
uh, I'm not aware of anything like that, but I haven't I haven't seen any papers like that. Um, if there is a published paper, I would love to read it, but I don't know anything about that. Dark matter is like a huge topic. So CMB can detect dark matter in a different way. So so one of the good candidates of dark matter is something called axion. Uh, Axion field. Axion field was like proposed for tackling an issue in something called CP violation. CP violation is a classic problem in our high energy physics. Uh, so axion is like a good candidate, and if there is an axion which can create certain signals in CMB, we could detect the dark matter, also dark energy. So CMB in the future experiments of CMB, we are really looking to shed some light on the dark sectors, assuming that the axion is a good dark matter candidate. But this paper, I don't know, and I'm not sure.
It was a question in the chat box. There is also another question in the chat box. Sir, can you suggest a good source to start learning about gravitational waves after learning basic general relativity?
Um, I would suggest the book Gravitation by Kip Thorne.
Okay.
Okay, I hope there are no more questions to ask. So to conclude,
Can I ask one more question?
oh, sure, sure.
Yes.
So when we speak about Big Bang, it is said that it's like the entire universe was 1 millionth of a pinpoint or something like that.
Yeah.
So why are we saying about this size? If the universe is expanding, it means that it originated from a single point, but the point can be a huge chunk of mass also, right? Why we say that it
Yeah.
originated from a single
Yeah.
very needle
Yeah.
point?
Yeah. That's a great question. I appreciate the question first of all. Um, but the question is wrong. Uh, why? Because it's like I have seen this thing like usually in the popular science talk. uh, that we had a single point origin, but that's not correct. There is no such as a single point. The expansion has happened everywhere. So even here where I'm standing, it has the Big Bang has happened. Even the point where you are standing, the Big Bang has happened. So it's not a single point. That's like a misleading analogy. I know I'm aware about the analogy. When we are like talking about the analogy, I know that there is a problem with the science thing, but don't take it as in a face value. That's not how the Big Bang happened. Big Bang has happened everywhere, every point. There is no such a single point. There is no special point. Assuming that there is a space, there was a space, or there was a sort of like higher dimensional space, uh, and it happened everywhere.
So it means that it was not from a, like, the universe is expanding not from a single point.
Not from a single point. Yeah, the space itself is expanding. So the point where we are standing is was also a part of Big Bang.
Okay, thank you.
So before concluding, there are a lot of students who are currently at their masters and at their bachelors listening to this talk. Can you give a bit of advice about how to move forward
How
in the
to
field of research?
yeah, uh, yeah, that I mean, if you could have, I mean, yeah, if you were like telling me before, I would have made a slide for that. Uh, but for sure, I can explain a bit. So, if you want to be continue the similar research in India, you have to go through the entrance exam, either by net or gate or I don't know whatever else now. Then you have to choose like a few institute. There are few institutes in India. One is IUCA, IUCAA, I think so, in Pune, and another one is Indian Institute of Astronomy and Astrophysics, IIA. Then there are certain ICES, the people who are working on cosmology and astrophysics. So you have to join there, and for the PhD. Um, that's one way if you want to continue your research on cosmology or astrophysics in India. Or if you want to go abroad, um, so if you want to target for US, United States, then you have to go through like GRE and all. But certain universities in states are not no more like want GRE. You can directly apply. If you are looking for Europe, I would highly recommend to do like a project which will be equivalent to like a publication, either like an equivalent publication. If you have like publication, it's excellent. So my personal experience, I did my master's uh, from SP College. After that, um, I started applying for universities in Europe, and most of one was like rejection. So I have counted like 70 rejection letters in my life. Uh, First of all, due to the lack of coursework of astrophysics in our curriculum, in SP College we never had like astrophysics coursework. So I cannot show anything that I am part of astrophysics. I know some basic astrophysics. So what I did, I joined uh, Center for Theoretical Physics, Jamia Millia Islamia, with a professor called Anjan Ananda Sen. I did a project on dark energy. I published a paper there. Then I got the DST JRF position in Kolkata, Presidency University. There I completed another paper. So after publishing these two papers, I started getting interviews. Before that, it was very hard to get an interview. Uh, so I would suggest to start doing some project when you are in masters. And if you want to really go abroad, do like a publishable work and add it to CV. That's one of the important thing. Um, yeah, after PhD, you have to go through like postdoctoral fellowships for a few years if you want to join for a faculty or something like that. I hope I answered the questions. If you want to um, discuss something personal, I mean, please feel free to contact me. I am already in the WhatsApp chat group. You can either message me or you can email me. And if somebody wants to are interested in doing some projects, feel free to contact. I can definitely suggest some projects. Yeah.
Sir, may I ask one thing?
Yeah.
Yeah, sir, like according to the concept till now we have developed in science and cosmology, what does it says about the time factor? Like initially, like when the Big Bang occurred before that, or at that time, does time existed, or it happened only after Big Bang? The time
So
factor.
the current best candidate is the time started at the time of Big Bang. That's a guess. Honestly speaking, that's a guess. We have no idea. We have no clue what's happened before. There are certain theories like in string theory. There are certain proposal. There are proposal of multiverse. There are multiple universe and universe get collide each other and new universe form. These are all possibilities, but we have no idea what happened before. We have to wait maybe for centuries. We might not have the answers in our lifetime. Maybe we will. Maybe we will never know. Yeah.
Sir, about the multiverse which you told, like it's a complete guess. Similarly, just like parallel universe. Like there is no factual even some some anything through which we can really connect it. I guess it's just an part of imagination, if I am right.
Not correct. It's not a part of imagination. It's a wild, educated guess. Uh, if something has happened, something like that, in a higher dimensional theories, something called topology defect can be happen, and this topology defect can be detected in CMB. So, but it's like a very high dimensional topic. I didn't want to go to that level, but anything such multiverse happened, the collision happened, there can be like certain faint signals which might be like able to detect, which uh, I don't know whether I don't have like a paper in my mind to refer right now. If you are mailing me, maybe I can find something for you.
Okay, sure, sir. Can I have your email address?
Shall I put it in the chat?
Yes, sure, sir. It will be great. Thank you. Thank you so much, sir.
Yeah.
I hope there are no more questions. So before we move on to the concluding part, let me kindly request every attendee to fill out a feedback form. The link is available in the chat box. Thank you. So to conclude this
Yeah.
amazing session,
Yeah, 1 second. So someone actually gave the paper by Catherine Freas and uh, Martin Wolfman, Dark Matter and the Gravitational Wave from the Dark Big Bang. Yeah, I was not known about this paper. Uh, Thank you for the recommendation. I will read it.
Okay, sir. So let me invite Siddharth sir, the Deputy Director of Poetry of Reality, for the vote of thanks.
Okay. Good evening, everyone. It is my honor and privilege to extend a heartfelt vote of thanks in this memorable occasion. First and foremost, I would like to thank Dr. Anto for his insightful speech. Your presence and contribution have truly enriched this event, and we are deeply grateful for the time and effort you have taken to be with us today. I express my sincere gratitude to Poetry of Reality for their dedication and meticulous planning, which have been instrumental in making this 5-5 talk series a grand success. I extend my heartfelt thanks to the technical and support staff of Poetry of Reality for ensuring that everything ran smoothly. Your seamless coordination is invaluable. To our participants, thank you for your enthusiastic presence and for making this event even more meaningful with your engagement and support. Your active participation adds value to our effort, and we appreciate your time and energy. We also conclude, as we conclude, let us carry forward the insight and inspiration we have gained from this 5-5 talk series. Once again, thank you all for being a part of this occasion. Thank you.
Thank you, guys. Much appreciated.
Thank you, sir.